Again, it's a rich thing.
What is going on, guys? Welcome back. In this beginner tutorial today, we're going to learn how to do statistics in Python. So let us get right into it. Alright, so we're going to talk about statistics in Python today, and my goal for this video is to give you both an introduction into the statistics module and also an understanding of what is happening behind the scenes. So I don't think that it is a valuable tutorial when I just import statistics and show you those are the functions, apply them, and this is what happens. I also want to show you a little bit of how things are calculated so that you can learn both a bit of Python and a bit of statistics. And as I mentioned, this video is more targeted towards beginners. So if all of this is way too easy for you, you can just watch another video. You don't have to watch it. This is targeted towards beginner programmers. So some of you might know that there is a Python module called math, so you can just import math, and this basically offers all sorts of mathematical simple functions. So math.sqrt, for example, for taking the square root, or math.sine for the sine function, cosine, or tan, or whatever. And then we also have x, and then we have ceil and floor and all that. So a bunch of basic math functions. However, the math module doesn't offer us stuff like taking the mean or the average of a collection or the standard deviation or something like that, because that is statistics and not what is included in the math module. So if we want to do something like that, we need to import the statistics module by saying import statistics. What happened now? Come on, statistics. There you go. And then we can use statistics dot whatever, mean, median, standard deviation, harmonic mean, and so on. And we're going to discuss those functions today, almost all of them, not exactly all of them, because there's one function I think that I have never used and I don't know where I should use it. But besides that, we're going to talk about all the functions here, and we're going to start with a very simple example here to just show you how things work. We're going to have a simple numbers list, and this numbers list is going to have the values 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. And now we can take the mean of that collection. Now the mean basically means the average value, average being defined as taking all the elements and dividing them by the amount of elements. So the average value doesn't have to be the value that occurs the most often. It just means that this value is somewhat in the center of the collection. And how you would do that without the statistics module is you would just take the sum of the numbers, so the core Python function sum, divided by the length of numbers, so by the amount of elements, and this would give you the simple mean of the collection. So sum of numbers divided by length of numbers is 55, because you basically take 10 plus 20 plus 30 and so on, divided by, in this case, I think we have 10 elements, right? So that is that, and we can also do that by just saying statistics dot mean numbers, which is the recommended way to do this. There's no reason to do it manually, especially because statistics is a core Python module, so you don't even have to install anything. You don't have to rely on external modules. Thus, just use statistics.mean. Now, if you want to get a different idea of the average, so you don't want to have the value that's somewhat in the center, you want to have the most occurring, not the most occurring, the value that is in the center, but not necessarily in terms of weight. So the difference, let me show you, the difference here is essentially right now the middle value, the center value is 55. Why? For multiple reasons. First of all, if you sum all those up and divide them by the amount of elements, you have 55. But also 55 is at the center of the collection. Now we have an even number of elements, we have 10 elements, so there is no real center value, because of course if we had now 110, the center value would be 60 because it's right in the center. We call this value right in the center the median. The median in this collection is the same as the mean because the values are evenly spread. It doesn't have to be the case, and I'm going to show you why in a second for those of you who don't know that. But essentially, if you want to have the value in the center, you use the median function. So using statistics, this would be just statistics median and that of numbers, and you will see that this is the exact same value as the mean in this case. However, for example, if I now change 100 to 1000, things change, because now you can see that 55 is still at the center of the list, right? The list hasn't gotten any longer. We don't have multiple elements. So if you go to the center of the list, you still have 55 in the middle. If you just take 50 and 60 combined, because you don't have, because we have an even number of elements here, we take the two center elements, we divide them by 2, and then we get the center value, so it's 55. If we have an additional element, it would be 60, but the value in the center doesn't change if I increase that number. I can even increase it to 100,000, nothing changes. However, the mean changes drastically because the sum changes. So the mean now is 10,045 because we sum up all these numbers and we have this huge outlier here, and if we divide by the amount of elements, we get essentially a larger number, but the position hasn't changed. So we still have the center value here. So this might be another notion of average. Another notion of average, and I'm going to tell you how to calculate the median here in a second, but another notion of average would be which value does occur the most often. So let's say I have something like a bunch of 10s here, and then we have the rest of the list being the same, and then I have, I don't know, a couple of outliers here, like huge numbers, I don't know, something like that. And then I run this, you can see here that the mean is very high and the median is 50 because that's the center of the collection here, that's the center of the list. But 10 would be in some way the average value because that's the value that you're most likely going to get if you just pick a random value. That's the average expected value that you get when you just pick one of those values because it occurs the most often. So that has the highest probability. And if you want to get the element that occurs the most often, you just use the statistics.mode function. So mode, the mode of a collection, the mode of a list gives you or is the element that occurs the most often. So in this case, 10. Now, I'm not sure actually what happens if you have multiple of those. What happens programmatically, because I think then you just have two modes, and it's just going to give you one of them. Okay. So let's get into the calculations. How do you calculate the median manually? Well, essentially you have a case distinction, so you have to say, okay, if the length of the numbers is divisible by 2, so if it's even, we need to take the center two elements and divide them by 2. How we do that is we take numbers, and then we take the length of the numbers divided by 2, floor division by 2, and then we add to that the position after that, or actually before that, and the result is then, so this calculation is just a simple addition, and we divide it by 2. We can print that, and you will see that in the even case, this is actually the same as calling the median function. And otherwise, if it's odd, if it's not even, we basically just take the center element, which is numbers, length of numbers, without the addition here, just divided by 2 minus 1. So divided by 2 minus 1 doesn't mean divided by 2 minus 1, so divided by 1, but divided by 2 and then minus 1. Obviously, I think that's basic math. Everyone knows that. And you can see that we get a problem here. Why do we get the problem? Let me just see what I messed up here. The median of numbers, and then we have numbers, length divided by 2 plus numbers length divided by 2 minus 1 divided by 2. And in this case, oh yeah, that was the problem. I looked at the wrong line. I was actually correct about this. We don't need the minus 1. There you go. So if we have an odd number of elements, we get into this branch here, just taking the center element, the element that is the length of the list divided by 2, so right in the middle. And otherwise, we take this element that is there and there. So if I remove this here, and I run this, you can see it's 45 because we take 40 and 50. None of them is in the middle because we have an even number of elements. So we take the center, 45. So we add them and then divide them by 2. So 90 divided by 2. And the mode is actually quite simple. We just count which value occurs the most often. So we basically just say, I think, how do you do that? You say max count or something. Let me just see if I wrote this down anywhere. Yeah, essentially what I did here in the prepared code is you take the max of the set of numbers, and here you pass the key argument saying that what is important is numbers count. So, sorry, not like that. The key is numbers count. So what we do is we take the numbers, we make a set out of them. A set, for those of you who don't know, a set means that whatever is in there is only in there once. So even if we have 4 10s here, we will only have 1 10 in the set. And because of that, we go through all the values, all the unique values, and we count them in the numbers list. And then we get the max value based on that count. And this is 10. So 10 is the value that gives us the highest result when we apply numbers count on it. That's the idea. And those are quite simple functions. Now, we have slight variations of those, so we can go ahead also, if we have a list like this one with even elements, we can also use the functions statistics.median high and median low. And I think those are actually, the names are actually quite telling already. So median high, median low. We're gonna get here 50 and 40. The median high is essentially if you have an even number of elements, and you don't want to do that division, you can either go for the high value 50 or for the low value 40. I'm not going to do the calculations here again, but essentially you just adjust. If you have an even number, you just pick the one that's larger, and if you have, or in the larger position, and if you have median low, you pick the lower one. That's the idea here. So now let us move on with the more complicated functions, at least when it comes to the formulas. The basic idea is still quite simple, but the formulas are a little bit more complex, and those functions are variance and standard deviation. And essentially the standard deviation is just the variance, the square root of the variance. So the variance is the standard deviation squared, if you want to put it like that. And thus they're mathematically almost the same when you write them down. There are differences. I'm not going to go into the differences here because that would go too deep into statistics and would go too far away from programming in Python. However, there are differences between variance and standard deviation when you use what, but the standard deviation is just the square root of the variance. The basic idea of those two metrics, of those two functions, is that you have a collection of numbers like this one here, and you have a certain mean. So you sum up all the elements, you divide by the amount of elements, and then you get the mean. And your question now, or our question now, is when you look at the individual elements, how far are those elements away from the mean on average? So you take for each of those, you want to know how far are they away from the average, from the mean, and then as a result of that, we get the standard deviation. So the standard grade of being away from the mean, if you want. So we can just go ahead and print statistics.standard deviation numbers, and we can do the same thing with the variance. There you go. You can see those are the values. And now if I just go ahead and say math.sqrt on the variance, you're going to see that we get the same value that we have for the standard deviation. So in fact, taking the square root of the variance results in the standard deviation. So let me show you how this changes. For example, let's change this list a little bit, or let's keep this but make another one. Numbers is equal to, and now let's use something like 0, 1, 2, 3 or something like that. And then we have something like 10,000, 20,000, 30,000. Now, if I print the mean of that collection, so statistics mean numbers, there you go. I have a mean that's pretty far away from all those values here. No value in this list is close to that mean. However, I can have a similar mean if I have something like, I don't know, if I have a collection 1,500 and then, I don't know, 8,500, sorry, 8,500 and 8,600. And then maybe I have also something like 8,550 and then 8,580 or something like that. So pretty close to the mean that we have in the first list. So if I now go ahead and take the mean of that, the mean is not too far away from what I had before. So let's rename those now to numbers 1, 2, numbers 1, numbers 2. Let's comment this out for a second here. You can see that the mean is not too different. Now, there is some difference, but it's not too different when it comes to the mean. However, the standard deviation is going to be very, very different. Why? Because in that collection, even though we have a similar mean to the collection down below, the problem is that all these values are very far away. 0, 1, 2, 3 are very far away from this value. And also those values are way higher than that value. Whereas in this list, each value here is quite close to the mean. So that is what we're asking here. And you can see that if we now print the standard deviation and the variance for numbers 1 and for numbers 2, we're going to get radically different results. So you can see here the standard deviation is a pretty huge number. This is the standard deviation. Here it's pretty small. Now, if you look into the documentation, you will notice that we have STDEV and variance, and we also have PSTDEV and p-variance. I don't want to talk about the differences here too much, but the mathematical difference is that when you talk about the variance, you divide by n-1, whereas dividing by n, it results in the p-variance, in the population variance, basically comparing to the whole population or to something else. Essentially, I don't want to go too deep into that, but we can see the difference here by just printing statistics dot PSTDEV numbers 1 and P variance numbers 1. Now we can delete that. And you can see that those values are not the same. They're quite similar. They're not too far apart, but they're not the same. And we're going to talk about the mathematical difference now because we're going to manually calculate the standard deviation now. We're going to say, and we're going to print the result, we're going to take the sum. Remember, what we want to do is we want to know for each element in that list, how far is it away from the mean. So what we're going to do is we're going to say for each x, I'm going to use a list comprehension here. So we're going to say x, and we're going to define what x is at the end or at later in that line. We're going to say x minus statistics.mean of numbers 1. So we take some element and we see how far is it away from that mean. And then what I do is I square that so that the difference is, it doesn't really matter if it's positive or negative. We take, we take the difference and we square the difference like that. And what we do then is we say the x is just an element or each element in numbers 1. So we want to take the difference between any number x in that list to the mean. We square that, and then what we do, actually, I again messed up the brackets like that. So we take the difference in parentheses, we square that difference for each x in numbers 1, and what we get out of here, we divide by the length of numbers. So let me just make sure I don't mess up this thing again. Divided by the length of numbers 1. So that thing here is now the variance if we don't take the square root. So that's the variance. And if we now go ahead and take math.sqrt from that, you can see that we end up with the values that we need. So first of all, let's comment this out here. So we get the PSTD, so the PSTDEV and the p-variance. This is what we get here. Now, if I want to get the normal standard deviation or the normal variance, I have to basically say length minus 1. So all I have to do is I have to copy that, I have to paste it, and in the end I divide by length of numbers 1 minus 1 and do the same thing here. Like that. Now we can uncomment this again. Maybe also change the order so that we get them in the same order. And then you can see that I messed up something. What is it? didn't close something here. Did I not close the print statement? Was it that? There you go. So now you can see that we get the respective values. So we can see here. Okay, now I'm a bit confused. Let me just add some more stuff here. Manual, and we're gonna call this manual. This is the standard deviation, so manual stdef, manual variance, manual pstdef, and finally manual p-variance. And then you can see that this value here is the same as this value here is the same as this value is the same as this value, and this one is the same as this value. So this is how you calculate that mathematically. You take the difference between any point and the mean, you square that difference, you sum it up, and then you divide by the length of the numbers list, basically by the amount of elements, and you can do -1 if you want to have the ordinary stdef function here, or variance, and you do basically just the amount of elements if you want to have the population standard deviation or the population variance. And for the variance, you take the square root. Actually, I messed this up again. This is stdef. This is the variance. This is the variance. This is stdef. There you go. Now it's right, because remember, the standard deviation is the square root of the variance. Now, last but not least, I want to show you the harmonic mean, and the harmonic mean is a mean that puts more weight on small values. So if you have small values in the collection, those values are going to attract the harmonic mean more than other values. So the mean just takes all the values, sums them up, divides them by the amount of elements, and the harmonic mean focuses more on small values. So if you have a 0, for example, in your list, the harmonic mean is automatically going to be 0. If you have very small values, it's going to gravitate towards those values. It's not going to pay too much attention to the large values. So this can be quite useful in machine learning, by the way, because sometimes you have certain functions where you want to optimize or regularize certain things, and you want to make sure that all values have a certain what would you say, that are high enough, if you want to put it like that. So you want to have certain weights for a function, and you want to make sure that not most of them are pretty high and some of them are low. You want to make sure that all of them have a decent level. And you can do that with the harmonic mean by making sure the harmonic mean is not too small, because if the harmonic mean finds one value that's small, it's going to gravitate towards that value, and we're going to see how that looks, or what that looks like. So we're going to say print numbers 1, actually not numbers 1, statistics dot harmonic mean numbers 1, and we're going to do the same thing with numbers 2. And you can see here, first of all, numbers 1, because we have a 0, it's automatically 0, but if I delete that 0, for example, you can see that it still gravitates towards the small values. Even if I add huge values here, it's going to gravitate towards the small values, no matter how large I make this number. You can see some things change here in the back of the decimal places, in the end of the decimal places, but the 3 is basically fixed. We focus on the small values. And you can see that here it's not the case. So if I have values that are roughly in the same space, it's going to still gravitate more towards the smaller values, but since they're quite equal, it's fine. You don't see that much of a difference. However, if I add something huge here, it won't really change much. Now, it changes something, don't get me wrong. We changed now from 8,000 to 10,000, but this number is huge, and we still just changed a little bit. So you can see it doesn't really change much more than that. It doesn't go too far away from that. And of course, if I add something like a 1 here, the whole collection is lost, because now the harmonic mean is 5. So this can be quite useful in certain scenarios, and the formula is not too difficult. It's essentially that you take the length of the list, so let's say length of numbers 1, divided by the sum of 1 divided by x for x in numbers 1. So essentially you take the amount of elements divided by, and then 1 over, this is why it puts so much weight on small values, 1 over the individual elements, and you sum those up. So you can see here, that is how we calculate the harmonic mean. And we can do the same thing with numbers too. So this can be quite useful. You can see those are the same values. So that's it for today's video. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.